race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. The wetsuit, from the Italian frogmen of World War II to the divers of today. The Aqualung, how fuel rationing led to leisure diving. Lipstick, Churchill's role in preserving women's beauty products. We reveal the amazing science and manufacture behind these wicked inventions. The modern-day wetsuit has become synonymous with surfers, kayakers and divers. They're a must-have for anybody serious about water sports, offering thermal insulation whilst not limiting movement. But did you know that without World War II, this body-insulating attire may never have come into existence? Diving suits in various forms have been around since the 18th century, but those were often cumbersome and limited the manoeuvrability of the wearer. In the 1800s, a German-born British engineer named Augustus Seeby developed a diving suit of canvas that would become standard amongst divers for almost a century. During World War II, the Thai company Pirelli developed a rubber suit that offered much better protection from the elements and even greater flexibility.
Italians started to use what were called frogmen, and they were the first to use wetsuits that were made of rubber. And it was also during the Second World War period that Neoprene was developed and discovered, and again this really helped to advance wetsuits as an item. These rubberized diving suits were the precursor to the wetsuit we recognise today. So, what's the science behind these suits, and what gives them their thermal insulating properties?
The water goes in between yourself and the rubber, and because water has a high heat capacity, once it's warm, it tends to stay warm. Rubber acts as an insulator, and so this water that's now warm against your body and against your skin allows you to stay warm in a colder environment, even though the initial jumping into the water could be quite cold and quite a shock.
Today, wetsuits are made of foam neoprene that hold bubbles of air within the material, significantly lowering the suit's ability to conduct heat and therefore keeping the wearer protected from harsh cold. After the war, these wetsuits began to find their way into popular culture and therefore began to grow in popularity amongst civilians, eventually leading to them becoming an indispensable bit of kit in water sports. From the coastal city of Ensenada, Mexico, O'Neill produced up to 200 wetsuits per day. The wetsuit starts off as a sheet of material called neoprene that O'Neill make themselves.
So neoprene starts out as a mix of what's called polychloroprene rubber. It's a synthetic rubber that is processed through a mixing process with different components that allow it to get baked later in the oven. So if you can imagine a loaf of bread, it starts out small, and then when you bake it in the oven, it grows, and that's exactly what happens with neoprene. So what happens when you bake that neoprene bun is that thousands of micro air cells integrated into the neoprene which provide the insulation for the wetsuit. So all these micro air cells are very, very small, but they fit together kind of like little bubbles of air inside the neoprene. The interesting thing about the neoprene air cells in there is it prevents water from entering into the neoprene and it prevents water from entering into your wetsuit.
Making these sheets takes up to 8 hours, and once complete, each roll goes through a visual inspection. The material is rolled over a lit screen so the examiner can check for any holes or abnormalities. Next, a designer uses Gerber pattern technology to lay out all the flat patterns of the wetsuit. These patterns are then printed onto paper and used to help cut out the material. Using this software cuts down waste, with the computer efficiently using all the material. Once the sheets are printed, they are then sent to the factory floor, where a worker places the paper over the neoprene material, adds weights and begins cutting out the desired patterns using a hand cutter. These cutters are so sharp, the operator has to wear a special Kevlar glove to protect his hand. Once the patterns are cut out, they are bundled and sent for marking, where they will be organised into sizes, depending on the suit.
The main purpose of a wetsuit is just to keep the user warm in any cold water environment. So the idea is just you want to have a layer of insulation against your skin that flexes with your body, moves with your body, and doesn't allow too much water in and out. So it can be used for any water sports purpose, any cold water application, even some warm water applications as well. The idea is just have something against your skin that won't rash you, that provides insulation for your body.
Now it's time for the branding and graphics to be added. Using a silkscreen printer, various cuts of the material are placed underneath the screen and ink is applied over the top. The ink is only allowed to fall through onto the material where the desired logo has been burned into the screen. The worker then moves the panel of material underneath a heater for a few moments to help cure the ink. The process is then repeated depending on the ink or desired pattern, where he would use a different screen. Next, glue adhesive is applied by hand using a brush to the edges of each neoprene cut. It is then applied 3 times to make sure the thickness of glue is sufficient to cover the entire seam of each cut. After several hours, the glue has dried and a worker now applies a chemical activator to reactivate the glue, which makes it sticky again. The worker carefully aligns each panel of material and presses them together by hand. Then, using a pneumatic crimper, he crimps the edges together to give a strong bond between each panel. After all the neoprene panels have been glued together, the suit is sent for stitching.
We've used wetsuits for so many different applications, and not just O'Neill, but I think many companies use wetsuits and neoprene for many different purposes. For example, we work with a research lab called Long's Marine Lab, and they do a lot of research with marine mammals, and we've made wetsuits for dolphins or beluga whales that they take down and take monitoring equipment down beneath the surface of the water. We've also made wetsuits for penguins because there's been some health issues with penguins that needed some sort of insulation. So it's being used for so many different purposes, and some really interesting applications out there.
Using a special blind stitch machine, the blind stitch does not fully penetrate the material, otherwise it would compromise the main waterproof features of the suit. Here, the needle and the thread only passes partially through, enough to create a strong hold, but not enough to penetrate the neoprene and create holes in the material. For a further layer of protection, a liquid tape is applied to the seams. Here we see a layer of liquid polyurethane being carefully applied by hand. This helps protect against the cold and adds extra waterproofing. Once the seals have dried several hours later, it is time for the finishing touches.
Wetsuits are a very difficult thing to make. They have to form fit to the body because if water gets in and you get cold. So they've got to be, the material that you use has to be lightweight and elastic. So you want it to be able to stretch and form over your body, but it's also got to be lightweight, and the most important thing that it's got to do is insulate your body from the cold. So the most important feature of a wetsuit is to move with the function of your body and also protect you from the cold water.
Here the zippers and all relevant labels are carefully added to the outer layer of the suit before being sent to quality control. The quality control manager then inspects each suit. He carefully tests the zip and Velcro seals, and finally adds a hanger and the final tags before personally taking them out and loading them onto trucks for distribution. The wetsuit, truly a wicked invention. We've seen how the creation of the wetsuit allowed divers to spend more time in the water, with their insulated clothing protecting them from the sea's cold embrace. But what about the not insignificant problem of breathing under the waves? For the pioneering divers of the 18th and 19th centuries, breathing underwater was as cumbersome as the equipment they were wearing. By the turn of the 20th century, the quest to develop an independent breathing system that allowed a diver to move freely from a supporting boat resulted in 2 main types of scuba, or self-contained underwater breathing apparatus, being developed. Open-circuit scuba, where the diver's exhaled gas is vented directly into the water, and closed-circuit scuba, where the diver's carbon dioxide is filtered from unused oxygen, which is then recirculated. The biggest problem for these early scubas was how to safely deal with the delivery of compressed air from a tank to the diver. The Aqualung, developed by a young Jacques Cousteau in France in 1943, answered this problem.
Very simply, an Aqualung is actually a big can of compressed air. What you have at the ends of the can is a valve and a regulator that allow you to not receive a huge blast of air into your lungs, which would basically make your lungs go pop. What the regulator does is it slows the air down to a pressure that you can breathe underwater.
Diving regulators had been in existence since the late 1800s, with the first successful open-circuit scuba developed in 1925. But there was a problem. The continuous flow of air limited how long the device could be used. The solution Cousteau and his engineer Émile Gagnan invented was a direct result of fuel shortages in occupied France. During the war, the Germans requisitioned petrol and many vehicles ran on gas. Engineer Émile Gagnan invented a demand regulator that would feed cooking gas to a car's carburetor in the exact amount needed. Cousteau took this new valve and used it to develop a new, simpler and safer scuba set that he called the Aqualung. That would ignite the world's passion in diving post-war in the 1950s and 60s.
There's quite a lot of popular films at this time that are released that have to do with diving or where the hero is a diver. And that means that people become increasingly keen to take up this new leisure activity. And obviously, as with everything, it means that there's a continuous development of the technology itself. So Aqualungs start off as a fairly primitive, crude model and then become increasingly sophisticated so that today anyone can don a pair of Aqualungs and go scuba diving.
Even though the Aqualung has allowed greater numbers of people to explore the depths, the inherent dangers of diving cannot be taken for granted. Possibly a diver's greatest fear is developing the bends. This is a potentially life-threatening condition that can occur if a diver ascends from the depths too quickly.
What happens when you're underwater is the pressure of the water is quite great, and in order to breathe, you need higher pressure air to breathe. If there's nitrogen in the air, which there is, 80% of normal air is nitrogen, this nitrogen actually dissolves in your blood. And the oxygen reacts with your blood cells to carry around so you can carry on normal functioning. But because this nitrogen dissolves in the blood, and is not normally dissolves in the blood, when you ascend from the depth, what starts to happen is the nitrogen starts to want to be released from the blood. In normal breathing, this would be released via your lungs. If you ascend too fast, the nitrogen starts to come out of your blood because the pressure from the water is less on your body, and actually it'll start to bubble up in your bloodstream at the point where it is. This results in essentially parts of your body inflating, and it's not good, it's actually quite painful.
The pain unfortunate divers experience led to the name the bends being given to the condition on account of victims curling up into a fetal position in a vain attempt to try and alleviate the excruciating symptoms. The technique to avoid the bends is for divers to slowly ascend from their diving depth, pausing a few times to allow their bodies to acclimatise to the pressure difference and allow the nitrogen to be expelled naturally from their body. With sophisticated closed-circuit scubas being the preserve of industry and the military, Cousteau's Aqualung has been instrumental in creating a simpler and safe way to explore the world's oceans, and all because of fuel rationing in World War II occupied France. We have just seen how successful scuba equipment was developed once air pressure could be controlled, and how the bends was caused by changes in water pressure on the body. Well, our intrepid tester is going to demonstrate the power of different air pressure. What you will need: some combustible material like paper or card, a lighter, a boiled and peeled egg, and a bottle. The problem: the egg is too large to fit into this bottle, but our tester thinks he can get it inside just by using the power of air pressure. The solution is simple. Our tester rips a piece of paper and places it in the neck of the bottle. He then lights it, pushes it into the bottle, and places the egg on top. And the egg is sucked in and it breaks. So, what happened? Let's watch it again in slow motion. We may not have been completely successful, but the egg was being magically sucked into the bottle. But how does this work? It is all to do with air pressure. When the lighted paper is placed in the bottle, it warms the air inside, which causes the air to expand and increase in volume. This expansion creates a greater pressure and leads to some of the air rushing out of the top of the bottle past the egg. Once the oxygen inside the bottle has been used up, the flame dies, which causes the air to cool, and this leads to a decrease in air pressure inside the bottle. In a reverse of the air escaping from the bottle when heated, there is now less air inside the bottle than there was when we started the experiment, and the outside air pressure is now greater and wants to get back inside the bottle. The force is so great that as the air tries to get back in, it pushes the egg inside the bottle, or, as in our case and the egg is too large, the pressure cuts the egg in half. So there you go, the power of different air pressures demonstrated by an egg and a bottle. Maybe use a smaller egg next time. A desire to improve and flaunt one's appearance may seem like a modern phenomenon, but humans have been image conscious for as far back as records go, and perhaps even further. We have evidence to show the use of early forms of lipstick that go back to ancient times.
And we also know that in ancient Egypt, Cleopatra in particular was said to love red lipstick. And it was often used from plants, flowers, and the juices of plants in order to provide a coloured pigment. Sometimes it didn't go very well because some of these plants were poisonous, and therefore women would put this red liquid on their lips, and it would prove to be fatal. And that's where the expression kiss of death comes from.
Fast forward to the 20th century, and lipstick becomes an even more prominent form of cosmetic. With the rationing in place during the Second World War, it may seem odd that cosmetics such as lipstick were exempt, but there was a very patriotic reason behind it.
There is a rumour, or an urban legend, that the reason lipsticks weren't rationed during World War II is that Winston Churchill himself decided that femininity was too important to the morale of the nation. One of the reasons that lipstick was seen to retain patriotic features was in the renaming of colours, particularly reds, to reflect themes of patriotism. So there was a patriot red lipstick or a fighting red lipstick.
Today the love of lippy continues, but what makes up a modern-day lipstick?
Beeswax, candelilla, canuba, all of these waxes are helping to the properties of being able to flow well and actually easily applied. You also then add in additives like amino acids, which help the lipstick actually bond to your lips, so that if it comes off, you still have a remnant of the dye, often a fluorescent dye, which allows it to appear bright and vibrant.
From ancient Egypt to inspiring patriotism during wartime, lipstick has a rich history almost as deep as its colour, and it seems set to continue as one of the most popular cosmetic products in use for years to come. Based in New York, USA, Colmar have been manufacturing beauty cosmetics for some of the biggest brands since 1921. Here they can make everything from skin, body and hair care products to colour cosmetics such as lipstick. Once an order for a batch of lipstick is received, all the raw materials are collected from the warehouse and, one by one, sent into a pre-weigh booth for weighing. These materials are scanned and approved to make sure they match the order on the batch card. Once everything is accounted for, the individual ingredients are added to various buckets, small tubs or little individual bags. They each have to be the correct weight, as anything over or under could spoil the entire batch. Over to the mixing room, where the initial base mix is being added. This is a mixture of wax and oils. The wax gives the lipstick its structure, and the oils provide the conditioning properties to the lip, as well as the release, which is the transition of the lipstick from the stick onto the lips. More oils or wax can be added or reduced depending on if the customer wants a hard or a soft lipstick.
In the 1960s, this facility was built and it's had a number of additions throughout the years. Our most significant addition being in the 1990s, where we consolidated both buildings into this building here. We service a lot of different technologies besides lipstick, but lipstick continues to be one of our top selling type products. And to this day, red is still the most popular color.
While all the base ingredients are being mixed, the colour shade of the lipstick is created at this point. The rolling mills run a combination of colour grinds and oils through the mill to evenly distribute the colour pigment. This must be completed before adding to the main mix to make sure the colour of the lipstick is consistent throughout the entire batch. The mixture goes through the rollers multiple times until it is the right consistency to travel through the other side and slowly drip into these pails. The new colour mix can now be added to the main ingredients, where it instantly has an effect by slowly transforming the colour. The final ingredient to be added is a sweetener, which masks the taste of the wax and the oil. Being a wax-based mix, the batch will be dropped into storage containers where it will solidify. In Colmar's development lab, a sample is tested to check the colouring and the shade of the lipstick. Personnel are trained to shade match under normal and UV light to make sure that the colour is exactly as ordered.
So the most important stage of the process is definitely the shading stage. It's the most complicated because at that point you have to get it very precisely to color as compared to the customer standard or the R&D standard that's been created for the lipstick. It's especially touchy because if you overshoot the lipstick, the batch will be blown and you have to start the process all over again.
Once everything is to the customer's satisfaction, it is over to the block moulding, where a bulk of the mix is transferred to a filling tank. Here, it is heated so it becomes a liquid again. Once turned, the bulk is pumped through 4 filling nozzles and into a mould. These moulds contain up to 4 different layers, with 72 cavities for the lipstick in total. The block moves at a slow pace because the bulk is a slow, solidifying liquid and can't be rushed, so we might have to speed this up. Once at the end, they are placed onto chilled tables for approximately 10 to 15 minutes. And once fully set, the top layer can be removed, so they can be moved onto the production line, demoulded, and individually placed into the base component. The lipsticks then make their way down the conveyor belt to flaming. This quick blast of heat takes away any imperfections on the lipstick and gives it a shiny, even finish. Workers then manually check for any remaining imperfections and swivel the lipstick down so it is ready for capping and secondary packaging.
So some of the challenges of making lipstick today is that consumers are looking for softer, more pliable lipstick because it has a better break on the lips. The issue there is that when you make a softer lipstick, it's susceptible to melting even at room temperatures and is a lot harder to insert by hand. So therefore it has to usually go into some sort of automated machine. And basically a softer lipstick is just a lot harder to manipulate and work with.
Colmar also have an automated lipstick filler, which in a similar fashion to the manual filling process uses a bulk base, which is removed by the machine. At the same time, a plastic puck holding 10 lipstick base components moves into place, where the machine picks it up, turns them upside down, while moving the lipstick into position and pushes it into the component base. The machine then retracts the component, complete with lipstick, and places them onto the same line, where they are then visually inspected. All the lipsticks now make their way to packing, where they are inspected first, before an automatic labeler stamps the shade label at the bottom of the lipstick. The finished lipsticks are then placed into individual lipstick cartons that are packed and sent to the customer. Lipstick, truly a wicked invention. So there you have it. A dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing background. The wetsuit, the aqualung, and lipstick. All wicked inventions.